Okay, so we're going to very quickly go through section 4.4. I promised you guys 6 minutes. Let's see if we can do it. It starts with the notion of what's called the indefinite integral. This is not the definite integral, this is the indefinite integral. The notation for this is that, okay? No numbers on the thing. This stands for the family of all functions. We'll call them big F, where the derivative of big F is equal to little f. Okay. Here's how we do this. So examples. So the first one we'll do very simple. Okay. So the family of all functions whose derivative is x squared. Well, we know what one antiderivative of x squared looks like. It's raise the power by 1 and divide by the new power, but we want all of them. So this can be any function where it's x cubed over 3 plus a constant. So this is any constant. And the reason for this is because the derivative of x cubed over 3 plus c, if you take its derivative, you get x squared, because that constant just vanishes. The derivative of a constant is 0. Another example of this would be a function like secant squared of x. Antiderivative of secant is tangent, and so we get tangent of x plus a constant. Another example of this, sine of x plus 2x. So an antiderivative for sine is minus cosine. Antiderivative of 2x is x squared, and then we have a plus c. So notice anytime you have an indefinite integral, anytime you don't see numbers there in the integration symbol, your answer should be a function, as opposed to when we put numbers in, your answer is a number. It represents the signed area under the graph of that curve. That is indefinite integrals. So let's talk about another part of this section, which is it's called the net change theorem. So we talked a little bit about this last time. Here's what it says. It says that if you have a definite integral of a rate of change, so rate of change, f prime is a rate of change, then this is by the fundamental theorem of calculus. Just take the antiderivative of f prime, which is f, and plug in b and a. It says the integral of a rate of change gives total change. Okay, that's what the statement says. Example. Particle, just writing down this problem might take more than 6 minutes. A particle moves on the x-axis with velocity. Here's its velocity function. V of t equals t squared minus t minus 6. And let's call this meters per second. Okay, part A. Find the displacement. So that is the difference in where it started and where it ended of the particle from time equals 1 to time equals 4. Okay, so the answer to this, well, net change, so we just integrate the velocity. So integrate the velocity, that is the integral from 1 to 4 of t squared minus t minus 6 dt, and this is t cubed over 3 minus t squared over 2 minus 6t, and we evaluate this from 1 to 4, and if you plug in 4 into this expression and plug in 1 into this expression and take the difference, then you get minus 9 halves. So that'll be in meters. So the particle moved 9 halves in the left direction along the axis from time 1 to time 4. Okay, let's do part B, which says find the total distance traveled from t equals 1 to 4. Okay. Okay. Now this is different than displacement. It's total distance. So we want to take the times when the velocity was negative and make it positive. So the way the answer to this is to integrate the absolute value of the velocity. Now if we take a look at the graph of t squared minus t plus 6, it looks like this. This is t squared minus t minus 6. So notice it's negative here and positive here. So the absolute value of this function will be, we're going to split this integral up. From 1 to 2, we will take the negative version of the velocity so that we count it moving forward. And then from 2 to 4, we will just take the positive version of the velocity so that it's moving forward. So this will make the area, which would be negative from 1 to 2 positive, and keep the area from 2 to 4 positive. So if you do this, and this is an exercise for you guys, you get 61 over 6, which is approximately 10.7 or so meters total. That's this section. We'll work on it in class.